Hello everyone. In today's lesson we're going to talk about interference and interference patterns. So the first thing we have to understand to discuss interference is that waves, unlike particles, can exist in the same space at the same time. If you think about something that is a particle, like a golf ball, two golf balls can't occupy the same space at the same time. They can't be superposed, as we might say. Whereas waves, like light or sound or even water waves, that wave energy can occupy the same space at the same time. So it's sort of helpful to think of a wave as a disturbance in this regard, especially if you're thinking about water waves. So if you have two water waves that are moving toward each other, those pulses, those disturbances in the medium of the water, they can exist, they can overlap in the same space at the same time, and that can cause the size of the wave to either increase or decrease depending on how the waves happen to overlap. And that's what we're going to be looking at here in today's lesson. So the first thing we need to understand about interference is that it can be constructive or destructive. So that is to say that when waves overlap and interfere, their wave effects can combine to cause constructive interference, or they can cancel to cause destructive interference. And we can have different degrees of constructive and destructive interference as well. So we're going to look at the different conditions for interference here in our discussion today. And we're going to start out with constructive interference. So constructive interference occurs when two in-phase wave pulses overlap. So we need to define this condition of waves being in phase before we can really look at constructive interference. When we say that two waves are in phase, there are a lot of different ways to define this or to think about the phase relationship of waves. We're going to keep it very simple. We're going to say that two waves are in phase if their crests overlap with each other and their troughs overlap with each other. So we're going to say crests overlap, crests, and troughs overlap, troughs. So that might look something like this. Let's get a different color. Let's say we have one wave like so, and then another wave that overlaps like so. So we have two crests in the same location, two troughs in the same location. Let's put an equilibrium line in here for reference. The result of this type of wave overlap is going to be an increase in the amplitude of each wave. So the interference pattern is going to have a larger amplitude than either of the individual waves, as we see here in orange. And the way we go about finding this interference pattern for constructive interference is pretty straightforward. We're just going to take the sum of the amplitudes of the individual waves. So let's write that out here. The amplitude of the interference pattern. Will be the sum of the amplitudes of the individual waves. And this is an application of what is referred to in physics as the principle of superposition. It's actually a vector sum, but because positive amplitude overlaps with positive amplitude, negative amplitude overlaps with negative amplitude, we're just adding the wave effects. We're adding the individual wave amplitudes to get the amplitude of the interference pattern. So let's walk through an example of how we might determine the interference amplitude for two in-phase wave pulses. So here we have two wave pulses. Let's say that the wave pulse on the left here is traveling to the right, and the wave pulse on the left, or excuse me, the wave pulse on the right, that is traveling to the left. So we have waves traveling in the directions indicated here. Oops. Let's get a grid for reference. So as these waves move, they're eventually going to overlap with each other in the middle of the screen. So the red pulse is going to move to the right. It's going to end up in this location. You know what? Let's not have me draw that. Let's use a shape so it looks a little bit nicer. There we go. So the red pulse is going to end up in the middle. The blue pulse is going to end up in the middle. Let's just say that the pulses are moving at the same speed. So like 1 grid per second or something like that, 3 seconds after the initial position, they're going to meet in the middle. So the blue pulse be right there like that. So here we see the wave pulses overlapping in the same space at the same time. They're in phase because these are two positive amplitudes, two wave crests that are overlapping. And so to find the amplitude of the interference pattern, we just have to add the individual amplitudes of the two waves. So if we count this in terms of the grid boxes here, it's an amplitude of just 1 grid box for the blue wave and 2 boxes for the red wave. 1 plus 2 would be 3. So our interference pattern, let's do that in a different color here, would have an amplitude of 3. So this is the result of the vector sum of the amplitudes of the red and the blue waves to give us the interference pattern here in purple. So that's a simple example of how we can determine the amplitude of an interference pattern for two in-phase waves that interfere constructively. So this is constructive interference. So next we want to take a look at destructive interference. So destructive interference is going to occur when we have two waves that are out of phase. So again, we're describing the phase relationship here as out of phase. There's a number of different ways we could define an out of phase relationship, but we're going to keep it simple. In the case of destructive interference, when waves are out of phase, we're just going to say that this involves crests overlapping with troughs. So this could be a situation, let's get a couple of example waves in here, where we have a wave like so, and then a second wave where trough overlaps with the crest of the first and its crest overlaps with the trough of the second. So these two waves would be considered to be out of phase, and they're going to interfere destructively. And in destructive interference patterns, we see cancellation of the wave amplitudes. These two waves seem to have equal and opposite amplitudes, so we're going to get complete destructive interference. The amplitude is going to be 0, which is really kind of cool. These wave effects are canceling each other out completely. So in terms of the principle of superposition for waves that are out of phase that are going to interfere destructively, the amplitude of the interference pattern is going to be the difference between the amplitudes of the individual waves. All right. So in this case, because the amplitudes are equal and opposite, the difference is 0. And the amplitude of the interference pattern, as a result, is 0. But once again, let's take a look at a little more detailed example here. Get a grid back. All right, so this time we have two wave pulses that are out of phase. One of them has a positive amplitude, that's a wave crest. The other has a negative amplitude, that's a wave trough. Once again, let's say that they're moving at the same speed. So they're going to meet here in the middle. So we've got an amplitude of 3 for that wave crest, positive amplitude, and then the trough, the other wave, negative amplitude of 2, like so here when they meet in the middle. So applying the principle of superposition, we're going to take the difference in the amplitudes. So we have an amplitude of positive 3, negative 2. That's going to leave us with a net amplitude of 1 for the interference pattern. And it's positive 1, so it should be a wave crest for that interference pattern pulse, like so. So this is going to be our don't want to write in triangles. This is going to be our interference pattern. And again, this is for destructive interference. Two waves are out of phase. And one thing that I should mention, I didn't mention this with the constructive interference example. So remember, in this example, our red wave is moving to the right, and our blue wave is moving to the left. Something really neat about interference in waves is that once these waves meet in the middle and they interfere, they create this interference pattern, they're going to go back to their original amplitude and direction of motion. They just move right through each other like nothing happened. So let's kind of rearrange things here. Oops, you know what? Let's not do that. Take that back. I'm going to get rid of my interference pattern here. So the waves are moving toward each other. They're going to meet in the middle and interfere. But then after they meet and interfere, they're going to keep moving in their original direction with their original amplitude. So let's say this is more time having elapsed. Let's say 3 more seconds have elapsed. So my red triangle is now going to be 3 more boxes over here. Oops, that's a line. Going to be 3 more boxes over here to the right, still moving to the right. And my blue triangle, going to be 3 more boxes over here to the left, still moving to the left. And notice that the wave pulses have gone back to their original amplitude and direction of motion. So they are acting as though nothing has even occurred, as though they didn't even interact with each other. They haven't lost any energy. They haven't lost any amplitude or speed or anything like that. They are unaffected by the interference that occurred in the middle of the screen earlier. So that's something to think about. This is true for all waves for the most part. They're going to be able to interfere and then be unaffected, pass right through each other, go back to their original amplitude and direction of motion afterwards. So we've looked at examples of in-phase waves, constructive interference, and out-of-phase waves, destructive interference. But what you're going to find with many cases of interference is that the waves are neither in phase nor out of phase, like the 2 waves that we see here. And we can still determine the interference pattern using the principle of superposition. It's just basic vector addition, where we're going to take the individual wave amplitudes and we're going to add them to get the amplitude of the interference pattern. Now, when we have a grid like this, I like to go point by point. We really only need to look at the area of overlap. So I'm going to focus on this area in the middle. Because outside of that space, the waves are not overlapping and they're not going to interfere as a result. So we're going to focus on that little space there in the middle. And we're going to go point by point. So we start right here, and we look at the red wave has an amplitude of positive 2. The blue wave has an amplitude of 0. If we do the vector sum, well, that's just positive 2. So I'm going to put a point right there. I'm going to go over 1 box to the right. At this point, we have a positive 1 amplitude for the red wave and a negative 1 amplitude for the blue wave. Now, positive 1, negative 1, that's equal opposite. Vector sum is going to be 0, so we're going to put a point at 0 amplitude right there in the middle. And then going to go one more point over. Now, the blue wave has an amplitude of negative 2, and the red wave is 0. So the sum would be negative 2. I'm going to put another point right there. And then once I've evaluated the amplitude of the interference pattern at each of the points of overlap, I'm going to connect the dots. So this is going to be a line, in this case, that's going to give me my interference pattern. So right there like that. That purple line shows me the interference pattern of these two waves. And then outside of that area of overlap, the amplitude is going to be the same. So we're going to end up with an interference pattern that looks kind of like this as a result of these two waves interfering at this particular instant in time. And note that this is not necessarily two waves that are in phase or out of phase. It's definitely more out of phase than in phase, but they're not perfectly out of phase. We can generally apply the principle of superposition to any two wave pulses, regardless of their phase orientation, to find the amplitude of the interference pattern, as I have done here. So it's a strategy that we can use to find the amplitude of an interference pattern for any two wave pulses, regardless of their phase relationship.